Okay, so I've got 6 o'clock, so we will get started. So I decided to do this on the intermediate value theorem since I don't have a video on that yet. So in order to kind of understand the intermediate value theorem, there is some information that would be very helpful. So we're just kind of going to go through definitions and things that you need to know before that. So this is a theorem that applies to polynomials. So we need to know what a polynomial is. So a polynomial function is just a specific type of equation where you have lots of terms added or subtracted, and all the variables have exponents on them, or you can have a variable with no exponent or have no variable at all, but it's basically just a series of terms added together, various forms of variables having exponents. All the exponents are whole numbers, all of your coefficients are real numbers, so there's no imaginary numbers in it. There's no square roots of variables inside them. There's no fractions with variables in the denominator. So polynomial is the basic thing, like we've talked about quadratic equations, those are polynomials, and linear equations are also polynomials. And then just some terminology. The term with the highest exponent is called the leading term. The number in front is the leading coefficient, and then that highest exponent is just the degree of the polynomial. But the intermediate value theorem applies to polynomials, so that's why you have to at least know what a polynomial is in order to use it. So the intermediate value theorem is this, basically. We have let f be a polynomial function. So it's just some equation that's a polynomial. For a less than b, if f of a and f of b have opposite signs, then f has at least one zero on the interval a to b. So when you're reading a math textbook or trying to understand theorems, it helps to break it apart and kind of draw pictures. So when we have functions, we're pretty much always looking at something that can be graphed on a grid, or on our XY plane. These functions are graphable. They have one input, one output. So we have for a less than b, and then f of a and f of b. So polynomial functions, if we're calling it f, that's f of x. So if we have f of a and f of b, then a and b are x values. So we have two x values, and it says a is less than b, so one of them is smaller than the other. So let's say I just label one of them a, and then the other one b. So we have a less than b, and it says f of a and f of b have opposite signs. So f of a and f of b are the y values, because when you have a function, your f of x is the y. So we're saying if the y values have opposite signs, so one is positive, one is negative. So let's say one is up here and one is down here. So we've got f of a and f of b. So they've got opposite signs. Then f has at least 1 0 on that interval from a to b. So this is part of a function. And so basically a function is just some graph, and we have these points connected. So a polynomial function is continuous. It has loops, or not really loops, but humps, and so I can connect them any way I want, but I have to connect f of a to f of b. And so it forces me to go across the x-axis there in order to connect f of a to f of b, because they have opposite signs. So we crossed the x-axis, and that is the location of a 0, because the 0 is where x is equal, or where your y value is equal to 0. So what the intermediate value theorem is saying is that if you have a y value that's positive and one that's negative, then when you connect them, because you have a polynomial function, it has to cross 0. Because in order to go from a positive number to a negative number, you have to cross 0 in between there. You can't jump, because then it's not continuous. A polynomial function is continuous. You have to connect them without lifting your pen or pencil. So the intermediate value theorem is just saying that there has to be a spot where y is equal to 0 in between these 2 points, because otherwise they can't be connected. And it doesn't matter whether the first value is positive or the second one is negative, because if I did the opposite here and I connected them, I'm still going to cross 0 here. So it doesn't matter which one is positive, which one's negative. As long as they're opposite signs, you have to be crossing y equals 0. So that's what the intermediate value theorem says. It just says you're guaranteed to cross 0 if you're going from positive to negative or negative to positive. Now, if you're going from positive to positive, you're not guaranteed a 0, because like these 2 points that I just put dots on, those are both positive. I don't have a 0 in between there. But I could, like maybe instead of going there, it went underneath and went back up. I could have a 0 there, but I might not have a 0 there. It's not guaranteed to have a 0. The only way we're guaranteed to have a 0 is if they're in opposite signs. So that's the intermediate value theorem. So why do you know this? You know, why do you need to know this? How is this useful, basically? This theorem is useful because we often try to find zeros of polynomials, and we use synthetic to do that with synthetic division, which I will talk a little bit about. But when you're trying to find zeros, if you know that you have to have a 0 between these two numbers, that helps you narrow down where it's located. So you're not just checking any random number. And this is actually, I took this from our textbook. So the intermediate value theorem can be used repeatedly in a technique called the bisection method to approximate the value of a 0. And this method is actually what your calculators do. Like graphing calculators, all the technology that we're relying on to find zeros actually use this method. So the bisection method utilizes a series of smaller and smaller intervals to converge on the location of a 0. So let's say I have my graph here, and I know that I have a 0 right here. You first have this larger interval, and you're like, oh, there's a 0 in between there. So now let's cut the interval in half and see, is there still a 0? And you just keep getting closer and closer, and you keep cutting your interval down by basically splitting the interval in half. What it's doing is it's like, okay, I have this interval. Let me actually use a different color. If I split that interval in half and then it checks either half, there's no 0 on the right, so then I split the left interval in half and I check either half. And then if there's no 0, I skip that, and then I divide it into half again. And you keep doing that until you basically find a 0. So that's what the bisection method does. This is what calculators do when they try to find zeros. And just as a point of interest, for my master's thesis, I wasn't finding zeros. I was finding something else called poles, which is actually zeros in a complex plane when we deal with imaginary numbers. So you have imaginary as your vertical and then real numbers as your horizontal. And so we're finding poles, which is sort of the same idea. And I didn't use this exact method because this is basically just looking at like a number line at this method. But what we did is we would do rectangles, and then we'd cut the rectangle into 4 pieces, check each rectangle, and then we'd keep iterating smaller and smaller rectangles until we found the 0 or the pole that we were looking for. And so this was an algorithm that part of my degree, you might think, oh, you're getting a math degree, a master's in math, but I actually did most of my thesis that I had to write was actually a program. So we basically wrote a computer program to do this. So math is actually a lot of higher level math you do is not actually math. You're writing computer programs. But that's what the intermediate value theorem is used for. It's used in calculators. It's used on computers. And if you're going into computer science or math, But you may actually have to program something like this. You might have to actually use the intermediate value theorem, like I basically did, but in a bigger context. So that's what this is. The rest of the thing talks about how humans have to do, it used to be done by hand, and now we've got computers to do it. Also, this last point here, and I'm going to highlight this, it talks about interpolation. And so for those of you that are going into engineering, there is, I believe it's ET 382 or 372. So one of the higher level math classes where you actually have to do linear interpolation, and you're basically finding the intermediate value between 2 points. So this is actually something you're going to have to use in one of your ET classes if you're in engineering. And I actually, we had some students that were struggling with that, so I made a video showing how to do that. So when you get to that class, that video should be in there and you'll see me again. So this is, kind of what the intermediate value theorem is, what it means, and how it's used. And I'm sorry, you're probably hearing the garbage truck come by. They're very late today, so very noisy day. Are there any questions so far? Okay, so moving on, we're actually going to use the intermediate value theorem to determine if there's a zero or not in the various intervals. And so to do that, the most efficient way to do that is to use synthetic division. So this is, so the intermediate value theorem is talked about in the first homework for the week. The second homework for the week is about synthetic division. But knowing some synthetic division makes the first homework go a little bit faster. So I'm going to do a little quick intro to this. And the way that the book is organized is it puts the synthetic division after the intermediate value theorem. It's like, why didn't it put that first? Because it would be helpful. But anyway, it doesn't. So we're going in the order of the book, which unfortunately makes things a little more difficult. So we're going to do this easier. So synthetic division. It is basically a shortcut to long division where all you need to do is multiply and add. You don't have any variables. You just use the numbers, and all you do is multiply and add. So this right here is your setup. So I set it up slightly different than the book does. I set it up more as a table, while the book sets it up sort of like what long division sets it up, but I find the table easier, especially if you're like trying to type something, or if you have like graph paper. I just find the table, setting it up like a table, easier for me. So your polynomial, you have your coefficients and you put them on the top right here. And if you don't have a term, you put in a 0. So if you're missing like an x squared term, you'd put a 0 there. And the first number always gets dropped down underneath it. And then the number you're trying to find the function value, like let's say you want to know what the y value is when x equals 2, you would put 2 right there. So you're given an x value, you're trying to find the y value. So that's sort of the setup. And then here, this is the process. So you multiply your first two things together, and then you write that answer up here, and then you add going down and you get a new answer. And then you repeat. So then you multiply these together, add, and you write that answer up here on top, add, and you get a new answer right there. Then you multiply again, put your answer up here, add going down, and then this last area on your table is your y value. This actually does work for linear equations. So let's say we have a linear equation, 2x plus 5, and we want to find f of -1. So normally you would just plug in -1 for x. So that would be 2 times negative 2 plus 5 is 3. It's easy enough when you have a linear equation to plug in a number for x, not a lot of work. If we were to do this with synthetic division, you would set up a table. I'm going to need more room. Let me move this over here. So we want to know what the y value is, goes with -1. So I have -1 in the lower left corner of my table, and the 2 gets dropped down, so I have 2 below. And then you multiply -1 times 2, which is -2. Then you add going down, -2 plus 5 gives you 3, and then that is your y value. So it looks silly to do when you have a linear equation, but it works really well with polynomials because it's faster. It usually deals with smaller numbers. It is far superior than what you would normally do. So I'm actually going to demonstrate this because you'll see that, oh my goodness, this is, this is really nice. So we're going to do it the normal way to find a function value, and then we're going to use synthetic division. So we have our function f of x equals x cubed minus 2x squared plus 5x minus 10. So that is, it's a polynomial function, and we want to find f of 2. And so to find f of 2, you're plugging 2 in for x, because if I've got x here and then I've replaced it with 2, everywhere I've highlighted also has to be replaced with 2. So that means I have 2 cubed minus 2 times 2 squared plus 5 times 2 minus 10. And then I need to follow the order of operations to simplify this. So 2 cubed is 8. Then I have minus 2, and I need to do 2 squared, which is 4. I can do the 5 times 2. So that would be 10, and then I've got my minus 10. Then I have 8 minus, then 2 times 4 is 8, plus 10 minus 10. And then 8 minus 8 is 0, 10 minus 10 is 0. This is going to be 0. We actually just found a 0. I actually made up that polynomial in that number. I didn't realize it was going to kind of come out to 0, so that was kind of cool. But that's what you would normally do if you're looking for a function value, is you'd have to plug in your x values, then you have to do follow the order of operations, and then you get your answer. Let's compare this to synthetic division. So along the top right, I put my coefficients. So x cubed doesn't have a number, so that's going to be a 1. Then I have my x squared, so that's -2. Then I have 5, and then I have minus 10. Then on the bottom left, we want f of 2, so I'm going to put 2 right there. And then the first column in that second row is 1 because it just drops down. So then I multiply. 2 times 1 is 2. 2 minus 2 is 0. Then I follow the process. 2 times 0 is 0. 0 plus 5 is 5. Then 2 times 5 is 10. 10 minus 10 is 0. And this is our answer. So I personally think that this went faster on the right, and it seemed like they were easy. It was easy math to do. It had a lot more zeros than the example on the left. I didn't have to deal with exponents like I did on the left. You don't have to think about the order of operations like you do on the left. You just have to multiply and add, and you get the same answer. It takes up almost less space too. So this is synthetic division. Now, synthetic division cannot be used for everything. It can be used for polynomials. So You know, it doesn't work for other things that like it doesn't work if you have square roots or absolute values. It only works on polynomials, but it is a nice shortcut when you're dealing with polynomials. Are there any questions on this slide? You wish you knew this before the first assignment. I agree. I think the book should have done this first. I don't know why the book has it organized the way that it does. But I think this is much nicer. And I'm glad to hear that someone else agrees with me. So, other questions or comments on this? Okay. So we're going to use synthetic division because it's going to make our life easier for these examples because it's so fast. So determine whether the intermediate value theorem guarantees that our function f of x equals 2x cubed minus 13x squared plus 18x plus 5 has a 0 on the intervals 1 to 2 and then from 2 to 3. So we're checking two different intervals here to see if there is a 0 in between. So let's first start with 1 to 2. So the way that the intermediate value theorem works is that we're going to have to find the function value for 1, and then we need to find the function value for 2. So we have to find function values for both endpoints and see if they're opposite in sign. If so, then yes, there's a 0. If not, we cannot guarantee that there is a 0 there. So here's how I'm going to set this up. And I use the table method because then I don't have to recopy my synthetic division. I just make a new row. So I just, kind of do them one on top of each other so I don't have to rewrite my stuff twice. I think that's an advantage of the method that I use to write it. And as long as you use a pencil, you can then erase, like kind of scratch work while you're doing this. So I'm going to just do the first row. So I'm going to do 1 times 2, which then gets written on the next one. 2 minus 13 is negative 11. Then I have 1 times negative 11, and that gets up on the next one. And then negative 11 plus 18, that's the same as 18 minus 11, that's going to be 7. And then 1 times 7 is 7, 7 plus 5 is 12. So f of 1 is equal to 12. So then what I usually do, because I do this in pencil, is I just erase that top row, and then I can move on and do the second row. So I have 2 times 2, which is 4. 4 minus 13 is negative 9. Then 2 times negative 9 is negative 18. Negative 18 plus 18 is 0. 2 times 0 is 0. 0 plus 5 is 5. So f of 2 is equal to 5. So this is how I set up my synthetic division, so I can save what I'm writing down. I don't have to show as much work. And when you get really good at it, you don't even need to write the stuff on top, because you can even just do it on a calculator. You just multiply and add and do it in one step with the calculator. So we have two function values here, and they're both positive. We have a y value of 12 and then a y value of 5. So it's conceivable that from 1 to 2, we just went from 12 to 5, and we just went down, and we did not cross 0. So we're not guaranteed a 0. Because You know, we could go straight from 12 to 5, not cross 0. You could cross 0 and have some wiggly stuff going on, but we can't guarantee it. So then we want to check two to 3. Oops, that's a bracket. And then this is great because I can just add 3 on to my existing table. And then I just need to check my second row, my third row there between f of 2 and f of 3. So I can just keep adding on to my table. I don't have to keep rewriting the synthetic division. So 3 times 2 is 6. 6 minus 13 is -7. 3 times -7 is -21. -21 plus 18 is -3. 3 times -3 is -9. And then -9 plus 5 is -4. So now we know that f of 3 is equal to -4. And now here we did change signs. We went from 5 down to -4. Let me rewrite that so it doesn't look like the equal sign. So we had to have crossed 0 to go from 5 to -4, which means that yes, there is a 0 in between there. We are guaranteed a 0. So I can even use this to kind of sketch. This is, you know, not to scale by any means. Definitely not to scale. But basically what we found is that we have a function value, we have an ordered pair 1, 12. And then at 2, we were at 5. And then 3, we were at -4. And so presumably, that was a really bad connection there. I'm not. Let's try that again. You connect these, and so we are probably crossing 0 at about 2.5. You know, we think there's probably a 0 around 2.5 based off of my picture. My picture could be, you know, wrong, but we know there's one somewhere in between 2 and 3. Because if you have to connect those points, you're going to have to cross the x-axis. Are there any questions? Okay, so I've got one more example because there's not really a lot we do with the intermediate theorem other than to see if there's a 0 to know whether we need to actually, you know, find a 0 there. So given f of x equals 9x cubed minus 18x squared minus 100x plus 200, determine if f has a 0 on the interval -4 to -3, and then if it does, find the 0. So to figure out if there's a 0, of course, we're going to use the intermediate value theorem. We're going to use synthetic division. So I'm going to set up my table, and I've got 9, -18, -100, and then 200 as my coefficients. And I'm probably going to need to use a calculator here because we've got some larger numbers there. And then I need to check the 2 points on the interval, -4 and -3. And the first part of our table is always dropping down. So the first column is just going to have 9s all the way down. So 4 times -9 is -36. And I probably could do that math in my head, but I could probably mess it up if I attempted that. So I'm using my calculator. Negative 54. Negative 4 times negative 54. So the nice thing when you do it on this calculator is you just take your answer and multiply by negative 4. So that gives us positive 216. And then even on your calculator, you just have to do minus 100. Like, it's super easy to do on a calculator. So that's 116. Then I multiply that by negative 4. That gives me negative 464 plus 200. And we get negative 264. Really, really small number, or a very negative number. It's a big number, but it's in the negatives. So now I'm going to just switch colors and repeat. So we have negative 3 times 9. And so it always helps me to erase this stuff. That is negative 27. And then negative 27 plus negative 18 is negative 45. Then I multiply negative 45 by negative 3. That comes to 135. Then I minus 100. So we get 35. Now I'm going to do negative 3 times 35. So I just take my calculator and multiply by negative 3. Negative 105 plus 200. And I get 95. So we got a negative and a positive. These are opposite signs. And so we have a 0 between x equals negative 4 and x equals negative 3 because they have opposite signs. So yes, there is a 0 in that interval, and now we need to figure out what that 0 is, now that we've determined that there is one. And so there are lots of ways to find that 0. In this case, we can find it by factoring. So we don't have to really do any guessing and checking because this particular problem is set up so that we can factor by grouping. So we can find the 0 by factoring. Once you kind of get into the synthetic division stuff, and I think it's like section 7.2, 7.3, you basically use some of the other theorems that we learned this week, and you guess and check, but you have possible zeros. So there's something called the rational zero theorem, which gives you a list of numbers to check. And then you check to see if those are zeros, giving you a y value of 0 when you plug it in, when you do the synthetic division. But in this case, because we're not focusing on those other theorems, this is a problem that we can do by factoring. So we're going to factor to find the 0. So I'm going to just start by rewriting our problem. And we're going to use factor by grouping, which is a good technique if you have 4 terms. And so I'm going to add a plus sign between the second term and the third term because that allows me to group and keep the negative with that second grouping. So we're factoring by 0, and since we're looking for a 0, we set this equal to 0. We're basically solving for x here. We're saying where is the y value equal to 0, or f of x equal to 0. That's what it means to be a 0. So I'm going to factor out the greatest common factor in the first pair. So I can divide a 9 out of the 9 and the 18. And I've got an x cubed and an x squared, and you always take the smallest exponent, so I can divide out an x squared. So when I divide 9x cubed by 9x squared, I'm left with an x left over. And then 18 divided by 9 is 2, and then I canceled out the x squared, so I basically removed that. Now I need to find the greatest common factor in the second grouping here. If the first number in that pair is negative, you're always going to factor out a negative. And then I can divide out 100 from both 100 and 200. And then because the 200 doesn't have an x, I can't remove an x. So I'm just literally dividing those by 100 when I'm factoring it out. So that gives me x minus 2. So the factor by grouping, we see that in the parentheses we have x minus 2. So that is one of our answers. That's one of the factors. And then the other one is 9x squared minus 100. So we've factored, but we have this 9x squared minus 100. We need to keep factoring. So when you're solving a polynomial, you often have to factor multiple times because you want to get them all down to x plus or minus a number. We don't want to leave it with x squareds. So the 9x squared minus 100, that's a binomial term of that is a difference of squares, because the 9x squared is 3x squared and then 100 is 10 squared. So that's a difference of squares, which is one of the special ways that we learn to factor. And seriously, we're going to be factoring and graphing stuff the whole rest of the class. So factoring is something that if you need to practice, definitely practice. So this would be 3x minus 10 and 3x plus 10. So you get a plus and a minus that cancel out when you multiply it out, and then you basically have the square root of each term. So now the zeros, as we're solving for x, we set each of these equal to 0. So we have x minus 2 equal to 0, which gives you an answer of 2. We have 3x minus 10 equals to 0, and when you solve that, oops, I wrote 10 equals 0. When you solve for x, you add 10 and divide by 3, so you're going to get 10 thirds. And then we have 3x minus 10 equal to 0. We add 10, divide by 3, we're going to get, oops, plus. I wrote a minus, it's 3x plus 10. We're going to subtract 10, divide by 3. That gives us negative 10 thirds. So we have 3 zeros for this function, but the question says find the 0 that is in the interval between -4 and -3. So 2 of our zeros are positive, which means they're definitely not between -4 and -3. The only one that is between -4 and -3 is the -10 thirds. That is basically -3 1/3. And that is between -3 and -4. It does fit in between that interval. So this is a use of the intermediate value theorem. We're basically saying, is there a 0 in between there? And then if so, we want to find that number. In this case, we were able to factor and figure out what number is in between there, what the actual 0 is in that interval. In other terms, you basically have to kind of guess and check, but you're guessing numbers that are within that interval. Like, it would be no good for me to guess the number 10 if I know there's a 0 between -4 and -3, because 10 is not between -4 and -3. It would just be a waste of time. So are there any questions? Looks good to you. Okay. So this is the intermediate value theorem. And the big takeaway, let me actually make sure that, yeah, I am facing me. The big takeaway that I would have here is this helps you narrow down what numbers you want to check when you're trying to factor or trying to find zeros of a polynomial. Now, in real life, the computer does most this, but there's the possibility that for your job, you may have to program the computer to do this. I mean, I never thought that I would have to do something like this, and then I ended up doing it to get my master's degree. So even if you may not actually have to do this in real life, at least you now know what the computer's doing, you know? And so, like, you know, a lot of math is a kind of what allows us to do things on calculators. And there's a potential possibility you might have to do this. Most of the time we don't do this by hand, though. Something you may do, you usually will just like graph it and then visually look where the zero is and then go from there. But this basically is just, you know, this is where the stuff comes from. This is how your calculator is doing things. If you've ever wondered, well, how does a calculator do this? Now you know. So it's kind of you're using technology that does algebra and you don't even realize it kind of thing. So I recommend for that first homework, go ahead and use the synthetic division to make your life easier. There's no reason not to. You know, even if it tells you to do it by hand or something like that, use the synthetic division. It's way faster. The second homework should be a little bit easier for you now that you've had some synthetic division, especially because trying to learn synthetic division from the textbook and from like written things is really hard, but seeing it in action is a lot easier. So hopefully, at least now that you've seen it happen, you're like, oh, that's what the textbook is trying to explain. So yeah, so glad that this was helpful for you guys and you guys were able to attend. And so I guess I will stop the recording and I will email this out to you guys tomorrow. So you guys have a great evening and I will talk to you later in the discussions or at the next live. So take care. Bye.